So you've seen Venn diagrams. I'm sure at some point in your life you might have forgotten about them, but these were named after a British logician and philosopher from the 19th century, John Venn. It's good to give credit to people because that is part of you're going to be producing really cool things as you go forward, and I hope to name you one day. So that's why I do that. All right. So in the universe of rational numbers, there are integers. We said that integers are all rational, and there are negative numbers. So Venn diagrams are described as follows. Typically, and you've already seen one. Oh, I was sneaking it in before I gave you warning. Um, but there's the big rectangle. Sorry, I could draw in here instead of using my hands, which I would normally do in a classroom. That big rectangle unit is defining that universe. So the universe is all the rational numbers. And obviously, I have not exhaustively listed all the rational numbers. I've given some examples of where things fit. I don't have time to list them all, obviously. But then we have a set, the set of negative numbers, and they are all, these are the negative numbers that are rational numbers. So we're only considering negative numbers within the universe of rational numbers, and that's important. Because okay, integers are all integers happen to be rational as well, so that's a bit different. But um, we define anything that exists in here as being both integers and negative numbers, and by default, they're in the big box. They are rational numbers as well. Okay, nothing's listed if it isn't fit within the universe. So pi is out here. Whoops, wrong screen. Pi is out here. It's not under consideration. It's not rational. E is outside of my universe. Okay. So let's go to the next slide. This will help. So the way that we write this out is we define the universe, and then we have sets, and we can have 3 sets, 4 sets, 5 sets defined. But if you have something within one of those circles or ovals, then they are members of that set. And if they're in B, if they're in the oval that is B, they are members of that set. At that point of overlap, it means they're members of both set A and set B. So if I go back a slide, right, -31 is an integer, but it's also a negative number. -5 is an integer, but it's also a negative number. And so it fits within that overlap. Okay, the numbers that are going to hang out over here, just in the blue, those are just integers. The numbers that hang out over here are negative numbers, but they're not integers. Okay, so all the positive integers over in the blue, all the negative non-integers are hanging out in the purple. Okay, so in this example, it means that they're an element in a set A, but not in set B. If they're in the blue only, then they're elements in set B, but they're not in set A. And the ones in the middle, in that intersection, those are elements in both A and B. So we saw that example of the negative integers on the previous slide. And anything outside of those ovals, those are elements that are in neither A nor B. Okay, so they're still in the universe, but they're not in A and they're not in B. So the universe we refer to as U, right? And we're using A and B to represent our sets. So the way that we describe those elements that are in a set A but not in B, we write that as A minus B. Elements in B but not in A, we write as B minus A. Elements in both A and B, we use this notation A intersect B. Raise your hand if you've seen this concept of intersection, and then if they're in either A or B. So anything that you find in any of the ovals, that's referred to as A union B, as listed on the bottom. How many hands are raised, Brent? I hope a few. Okay, that's fair. And then finally, elements that are in neither A nor B, it's the universe minus everything found in any of A or B.